Okay, good afternoon to everybody. The speaker of today is Alessandro Scagliotti, that is a postdoc at the Technische Universität of München. And formerly, he was also a PhD student here at SISTA in the AMA group. And today, he will speak about a principle for minimizers of regularized functions. So Alessandro, when you're ready, you can start.
Okay, perfect. Okay, thanks everyone. Thanks Laura for chairing this session. So as Laura said, we are going to see a quite general principle for minimizers of regularized functionals. Okay, so the outline of the presentation is the following one. We will see this principle in, let's say, the basic statement of this principle that at first glance, at least to us, sounded quite unexpected. Then we will see a couple of examples, and then we will move towards possible generalizations and extensions. Okay, so as always, feel free to interrupt me at any point of the presentation. You can ask questions at the end, but also during. For me, it's not a problem. Okay, so let's give a little bit of motivation. So let's assume that we wish to minimize a certain functional, in this case h, in the decision variable theta. Okay, so I've written down the typical problem that arises in data science, but you can really think about something extremely general. Could be also a problem arising in calculus of variations, and the only point is that this functional consists of two terms. The first term is a sort of in applied mathematics could be called a data fidelity term. So it's something that is somehow enforcing, in this case, the fact that phi theta is interpolating some data. While the second term is a regularization term that, for instance, in calculus of variation is responsible for providing coercivity. While in applied mathematics is somehow used for enforce some prior knowledge in the parameter theta. For instance, in regression problems, reg theta may somehow enforce some sparsity in the decision variable theta. Okay, a crucial role will be played by alpha. Alpha, still using again the language of machine learning, is a hyperparameter, so it's something that is chosen at the beginning. So is a constant that is in charge of tuning this regularization. So the higher is alpha, the more importance we are giving to the regularization term. Okay, so if we think about non-convex problems, and this is typically the case in modern applied mathematics problems, for instance, arising in the training of neural networks. So here phi theta may represent a neural network, and theta is the collection of all its parameters. So in such problems, in such optimization problems, typically the objective function h is non-convex, and we may expect multiple global minimizers. Okay, so the claim, the statement of this trade-off invariance principle that we're going to see is the following one. Okay, so we're going to see that for typical values of alpha, and then we are going to be more precise later on what I mean by typical values. It turns out that given any two theta 1, theta 2 minimizers of h, we have the following three identities. Okay, so the first one is trivial, right? It comes simply by the fact that both theta 1 and theta 2 are minimizers of h. The interesting one are the other two. Okay, so the point is that a priori is never clear, is not clear, is not in general, and indeed in general it's not always true, that the value of the first term coincide on the two different minimizers as well as the value of the regularization. But this is indeed actually the case, I stress it once again, for typical values of alpha. Okay, so we are going to make this precise in a second. Okay, so now since the principle is rather general, we can let me state it in full generality. Okay, so what we need is a domain U non-empty, a non-empty domain, and we don't need to ask any further structure on that. So we don't need to put any topology on U. It's just a set. Then we have F and Fg that are two assumptions, and once again, we are not going to require any assumption on F and G, except the fact that they are taking values in R. Okay, so the principle holds also if we allow for values in the R extended. So if we also allow plus infinity. But for simplicity, let me just say that in this presentation, F and G are taking values in R. Okay, as said before, H alpha is the weighted sum of F plus alpha G, and G can be thought as a regularizer, but once again, we are not, G is not having any further property with respect to F. So if not the fact that is multiplied by a non-negative parameter alpha. Okay, so the further assumption that we have is for the first part of the presentation is the following one, that there exists a B that will be the extremes of an interval in which the problem of minimizing H alpha has a solution. So we will assume that when alpha is running in a certain interval AB, the set of minimizers is non-empty. Okay, and now I'm ready to state again in an informal way the trade-off invariance principle. So the trade-off invariance principle is indeed saying that excluding only few unfortunate alpha, we will quantify them a little bit later. We have that given any two minimizers, U star 1, U star 2, belonging to H star alpha, of course, alpha in this case is fixed, we will have that F evaluated on U star 1 and evaluated on U star 2 is the same, as well as G. Okay, so the values of F and G will agree on different minimizers of H alpha. Okay, so at least this statement to us was looking a little bit surprising, but indeed the way of proving that is first showing a lemma whose statement is on the other end much more reasonable. Okay, so indeed the title in the next slide, only the title is changing. So instead of an unexpected fact, now we just have a reasonable fact. Okay, so the framework is exactly the same as before, but now this is the key lemma that will play a crucial role for the trade-off invariance principle. Okay, so the key lemma is investigating the role that has the parameter alpha on the values of the regularizer. Okay, so let me be more precise. Let's choose alpha 1 and alpha 2 in this interval where we know that the minimization problem has solution. Okay, so and let's assume that alpha 1 is smaller than alpha 2. Okay, so what does it mean? It means that when alpha, so if alpha 1 is smaller than alpha 2, then we are giving less importance to G in this trade-off. Okay, so then what we expect that on the minimizers, if alpha 1 is smaller, the value of G will be bigger because we are giving less importance to the minimization of G. Okay, so this is precisely what is claimed in this chain of inequalities. Okay, so once again, we have an inequality that is trivial. Okay, so in all this inequality, only G is concerned. Okay, so the second inequality, which is the trivial one, we have that the supremum is bigger than the infimum when computed on the same set. Okay, so nothing to say on that. The interesting inequality is the first one. This is saying that when alpha 1 is smaller, then the minimizer of H alpha 1 that has the lowest value in G is always going to be big, the value of G on that guy is always going to be bigger than the supremum of G computed on all the minimizers related to alpha 2. Okay, so this phenomenon is pretty natural and is related to the fact that we said at the beginning. Okay, so when alpha 1 is smaller, we are giving less importance to G in this trade-off. Okay, so if you believe this lemma and if you are curious about the proof, it's quite basic and I have a slide at the end of the presentation. Then we have okay, so if you believe this, let's say, quite reasonable lemma, there are two important consequences. The first one is that the function that is mapping alpha into the infimum of G computed on H star alpha is monotonically non-increasing, right? This is precisely coming from this inequality, from the first and the last element in the inequality. And the consequence too, which is the crucial one, is that when dealing with monotonic functions, we always have that excluding at most countably many values of in the domain, the function is continuous. Okay, so this is, and now we are in position for stating the formal statement of the trade-off invariance principle. Okay, as you may guess, now we can quantify the number of bad guys, and the bad values of alpha are at most countably many in this interval. Okay, so if we exclude at most countably many bad guys, for all the others, we have that. If we take any two minimizers of H alpha, the value of F on all the minimizers is going to agree as well as the value of G. Okay, so let's prove that. It's a few lines proof. Okay, so we assume that we have a value of alpha, a certain value alpha bar, in which the trade-off invariance principle is violated. So it means that there exist two guys, two minimizers of H alpha bar, such that the G disagrees on these two minimizers. Okay, cool. Then what happens? Then it happens that the supremum of G, since G is non-constant on the set of minimizers, we have that the supremum is strictly bigger than the infimum. Okay, but now what happens? Now let's take any alpha running from A, which is which was the extreme from which we know that there exists minimizer, to alpha bar. Alpha bar excluded. And owing to the monotonicity lemma that we have seen before, we have this chain of inequality. Okay, and the last inequality is satisfied with is strict. Okay, then we can pass to the limit. Okay, so we pass to the limit in this inequality, and hence the strict inequality is preserved because we pass to the limit here. And what we get is the following one. Okay, so we get that the left limit as alpha is going to alpha bar is discontinuous. Okay, so the function that is mapping alpha into the infimum of G computed on H star alpha as a discontinuity point at alpha bar. Okay, but as said before, G is monotonic, hence we may have at most countably many discontinuity points. Okay, so what the proof shows is that if we are in a point where the trade-off invariance principle is violated, then this function is discontinuous. Okay, and hence could only happen at most countably many times. Okay, so this is the end of the proof of the basic statement of the trade-off invariance principle. Now, we can see some examples, some possible applications before passing through to the extensions. Okay, so let's imagine. So so during my PhD, I mostly worked in optimal control problems. So let's so the first example I could come up with is a constraint optimization problem inspired by optimal control. So let's imagine that we want to minimize a function f subject to the hard constraint that g of u must be equal to z. Okay, in our case, u is the decision variable. Okay, so we may imagine u as the control that is driving a trajectory, and gu equal to z means is somehow encoding in an abstract way the fact that at the terminal point the trajectory should arrive to a submanifold. Okay, so this is an hard problem, and hard constraint optimal control problems can be painful to handle because it could be hard to arrive precisely at the prescribed manifold. Okay, so what is the typical strategy? The typical strategy is to penalize, to allow for violation of the final constraint and to introduce a soft constraint. So basically, soft constraint means that we are somehow incorporating the constraint into the objective function, and we multiply it by a weight that is the higher the higher is the weight, the more importance we give to the violation of to the violation of the constraint. Okay, so the typical picture that I had in mind was the following one. So imagine that we solve this problem and that we have multiple solutions. So this might be often the case if this could be a typical case if the optimization problem here is non-convex. And the typical picture that I had in mind was the following one. So imagine that we find the two optimal solutions. It may happen that, for instance, the first one is the blue trajectory is shorter, so we have a smaller value of the fuel consumption, say, but we arrive more far away from the constraint, so we pay more in terms of the violation. Okay, another optimal control could be for the same function, could be the red one, in which, for instance, we consume more fuel, but we arrive closer to the target. Okay, so indeed, in the case of multiple minimizers, the trade-off invariance principle is claiming that this is not the typical picture that we should have in mind. Indeed, what is actually happening is something like that. So if we have multiple solutions, then they will violate, for typical values of alpha, of course, they will violate the soft constraint for the same amount. Okay, so they will, in this case, the two trajectory will arrive on the same level set of the function responsible for penalizing the constraint. Okay, so the second example is concerns the exceptional alphas. Okay, so the statement was telling us that we may have at most countably many exceptional alphas. So a natural question that we may ask is, can we cook up some examples in which we actually have infinitely many values of alpha? And the answer is indeed positive. Okay, so the example is the following one. Okay, so we use as a domain the positive real line. Then we use as a function f this series of functions. Okay, so this is just a fancy way of writing something very elementary. So the function f is a piecewise linear function that has a slope 1 in the interval 0, 1, slope 2 in the interval 1, 2, and so on and so forth. And as a function g, we are going to use minus u. Okay, so we are going to cook up the function h as f plus alpha g, as usual. Okay, so this is what is going to happen. When alpha is running between 0 and 1, we have that the set of minimizers is reduced to the unique point 0. Okay, so when we have just one minimizer, the trade-off invariance principle is trivially satisfied. So because it's saying that for every choice of U1, U2 in the minimizers, but if we just have a single one, basically there is nothing to choose, and the trade-off invariance principle holds. Then what happens? Then when alpha is equal to 1, basically the slope of alpha g is aligned with the slope of f in the first interval, and it turns out that the set of minimizers of h alpha is the whole interval 0, 1. Okay, so we have all these points in which we have a minimizer. Okay, of course, in this case, the trade-off invariance principle is violated because the function g is not constant on the interval 0, 1. Then what happens? If we choose alpha any value to be any value in between 1 and 2, we have that the picture of the graph of h alpha is the following one. And we will have once again that the minimizer is reduced to a single point. and this single point is 1. Okay, then what is going to happen? As you may imagine, whenever alpha is in between two integers without extreme excluded, we have that the set of minimizers is reduced to a single point. Okay, and hence the trade-off invariance principle holds. But whenever alpha is an integer, we have a violation of the trade-off invariance principle, and as the set of minimizers is a whole interval, and G is non-constant on the intervals. Okay. Of course, this is an academic example. It's not something coming from applications, but it's basically showing that we may construct also pathological situations in which we have actually infinitely many bad values of alpha. Okay. Now it's so if there are no questions, and always feel free to interrupt and ask, we can start the section concerning the extensions. So the first extension concerns the multi-regularized functions. Okay, so what does it mean? It means that we have f as before, which is essentially the main term that we are interested in. But of course, at least from the theoretical perspective, there are no asymmetries between f, G1 and G2. Okay, so it's we may psychologically think f being the most important object in our minimization, but from the theoretical viewpoint, there is no distinction between f, G1, and G2. Okay, so the only difference is that now we do not have just f and g, but we have f, for instance, G1 and G2. Okay, so we can consider here, I'm going to consider for simplicity the case of two regularizers, but as you may imagine, two or more regularizers is the same. Okay, so similar framework as before. So f, G1, and G2 are defined on a very generic set U. And this time alpha is made of two components, alpha 1 and alpha 2, both taking values in 0 plus infinity. Okay, the functional alpha now consists of three terms. The main term f, then we have alpha 1 G1 and alpha 2 G2. The natural question is, okay, so is the trade-off invariance principle still true in this case? There is any hope? Okay, so the academic example can help us to understand a little bit better the situations. Okay, so the point is that we cannot expect anymore to just have countably many exceptions. Okay, so let's explain why. Okay, so let's think to the same exact framework as in the example 2. We have U being the positive half line. We have F defined as the piecewise linear function. G1 is minus U. And G2 is very stupid. It's identically 0. So it's playing no role. Okay, so since the situation is identical to the previous one, we have that the principle is violated whenever alpha 1 is an integer. Okay, but alpha 2 can be anything, since basically it's playing no role. So we have a violation of the principle whenever k is an integer, a natural number, and for every value of a in 0 plus infinity. So basically for any value of alpha 2. Okay, so as you may see, these we have uncountably many of them. On the other hand, all these bad values are lying. So if we imagine to place them in this subset of R2, all these bad values are lying on vertical lines, okay, on countably many vertical lines. And so despite the number of points is uncountable, countable union of lines as Lebesgue measure 0. So we may conjecture that the trade-off invariance principle is true if we choose, so if we exclude a Lebesgue negligible subset. Okay, so and this is indeed actually the case. So the formal statement for the multi-regularized trade-off invariance principle is the following one. So for L2, almost every choice of alpha in 0 plus infinity squared, what we have? We have that if H alpha, so whenever we pick U star 1, U star 2 minimizers of H alpha, then we have the three chain of inequalities. So F is constant, G1 is constant, and G2 is constant on the minimizers. Okay, so let's look at the proof. Once again, it's the proof with the proof of the idea is 3 line longs. Okay, so what is the idea? The idea is that we should apply Fubini. Okay, so if we apply Fubini and we keep alpha 2 fixed, then we can merge the term alpha 2 G2 with F. Okay, and then we are in the single regularized case in which the only regularized term is the second one, is alpha 1 G1. Okay, so in this case, we have that the exceptional for alpha 2 fixed, the exceptional alpha 1s are at most countably many. Cool. But what does it mean? It means that the Lebesgue measure of the slice is 0 because it consists of at most countably many points. And then if we do the integration along every possible slice, we deduce that the exceptional alphas for which the trade-off invariance principle is violated this set is Lebesgue negligible. Okay, so all these argument works provided that we are able to show that what we want to measure is measurable. Okay, indeed, the hardest part of the proof is the measurability of the set of the exceptional alphas. Okay, so I think that I have a little bit of time, so I will try to sketch it. Okay, so what is the key idea behind this measurability proof? So this is another point that is a little bit surprising because we are doing no assumptions on F, G1, and G2. Okay, F, G1, and G2 are not assumed to have any measurability assumption, and indeed U is a set which has not a measurable structure itself, right? It's not a measurable set. However, the point is that we are not claiming or trying to prove measurability of these functions. What we are interested is not the dependence in a U, but rather the dependence of the problem in alpha. And in alpha, we have a lot of structure because alpha is a subset of 0 plus infinity squared. Okay, so this is more or less the idea. Okay, so what's the point? Just recall the notation. H alpha is the weighted sum of F, alpha 1, G1, alpha 2, G2. And just for a simplicity of exposition, let's assume that H alpha admits minimizer for every value of alpha in 0 plus infinity. It's not really necessary, but let's assume it for simplicity. Okay, so what we do? We introduce the following functions. So we introduce the function G1 plus alpha that is doing what? That is computing the supremum of G1 over all the possible minimizers of H alpha. Okay, so G1 minus is computing the infimum of G1 over the minimizers of H alpha, and similarly G2 plus and G2 minus computed at alpha. Okay, so what's the point? The point is that the bad values of alpha are contained in this set. Okay, so the bad values of alpha are those values for which the trade-off invariance principle is violated, which means that either G1 plus and G1 minus disagree, or G2 plus and G2 minus disagree. Okay, so essentially this is the set that we would like to measure. What is the lemma that we prove? The lemma that we prove is essentially is a measurability, is some regularity of these functions G1 plus and G1 minus. what we have is that G1 plus is upper semi-continuous, and indeed is slightly more than upper semi-continuous. Upper semi-continuity here would like to have simply a greater or equal. But here we have an equality. And similarly for the other one. So we can say that all the functions listed here, listed above, are either lower semi-continuous, so the guys with the minus are lower semi-continuous, and the guys with the plus are upper semi-continuous. Okay, so this is enough for saying that these sets are Borel measurable. And hence the set of the bad guys that we want to measure is indeed measurable, and so the proof that I showed you before is actually working. I was not completely cheating. Okay, so now it's time for other extensions. So the next extension concerns the minimizing sequences. Okay, so far we have worked always under the assumption that H alpha had a solution. Okay, so that for certain values of alpha, at least ranging in some sub-interval, we were able to find the minimizers. Okay, so this assumption indeed is not necessary. And indeed we can prove a trade-off invariance principle for the minimizing sequences. Okay, so this is the point. Okay, so we always need to exclude at most countably many values of alpha. Okay, so this is unavoidable. Then what happens? If the infimum of H alpha is bigger than minus infinity, then we have that for every alpha, there exist two values, f at alpha and g at alpha, such that given any minimizing sequence, the value of f computed along the minimizing sequence is converging to f at alpha, as well as the value of g computing along the minimizing sequence. Okay, so what is crucial is that these values, these limiting values of f and g, do not depend, of course, on the minimizing sequence. So it's not a theorem that is stating that along minimizing sequences, these limits exist, but they are saying that there exist two constants for which the limits of f and g evaluated on the minimizing sequences exist and is always equal to these constants. Okay, this is the statement for the minimizing sequences, and here we have okay, and we have what is the idea for proving that? So if once again this result seems unexpected and maybe too powerful, too strong for being true, it's once again follows from a much reasonable result that is a generalized monotonicity lemma. Okay, so essentially what's in a nutshell, how do we define these objects, the objects involved? So S alpha is the family of all the minimizing sequences for the functional H alpha, and we define G plus and G minus as the supremum of the lim sup of G computed on the minimizing sequence, and G minus as the infimum of the lim inf of G computed on any minimizing sequence. Okay, so similarly, so with an argument that is exactly the same as the monotonicity lemma 1, it's possible to prove this chain of inequality. Okay, so once again, we have two inequalities that are trivial, which is the two inequalities at the extreme. The only interesting one is the one in the middle. Okay, the interesting inequality is telling you that what happens if you take alpha 1 to be strictly smaller than alpha 2. And this once again is the key for proving the trade-off invariance principle for minimizing sequences. I don't want to stress too much into these details. Okay, I want to present a corollary of the trade-off invariance principle for minimizing sequences. So this is something that is that may happen quite often in calculus of variation. So whenever you apply the direct method of the calculus of variations. So let's imagine that U is a uniformly convex Banach space. For instance, LP with P running from 1 to infinity. Extreme excluded. And let's consider F to be the functional of interest and G to be the norm of U. This works even if G is not just the norm or is the norm to some power P. For instance, the norm 2 to the power 2 or the norm P to the power P. Okay? And let's set H alpha be written like that, be as usual, F plus alpha times the norm of U. Then what happens? Then if we exclude at most countably many bad values of alpha, if the infimum is bigger than minus infinity, what happens? Imagine that we produce a sequence that is weakly converging to a minimizer, and that, we have a sequence that is a minimizing sequence and that is weakly converging to a minimizer. Okay, so this is the typical picture that happens when we apply the direct method of calculus of variations. Then it turns out that the convergence, the weak convergence, is for free a strong convergence. Why? Well, because we can use as we can apply the trade-off invariance principle first to this minimizing sequence, and then to the minimizing sequence, which is identically equal to the minimizer U star. Okay, so in this way, what do we get? In this way, we get that these sequences may have the same limit when we take the norm on them, and this implies that we have weak convergence of the sequence plus the convergence of their norms. And this, in the uniformly convex Banach spaces, is enough for concluding that we have a strong convergence of the sequence. Okay, so we also have something a little bit more. So if H alpha is sequentially weakly lower semi-continuous, then for every minimizing sequence, what we have is that the minimizing sequence is weakly per-compact if and only if it's strongly per-compact. Okay. Okay, so in the same situation, we also have a negative result. So let's assume that we are in the same situation as before, so uniformly convex Banach space. And let's now consider a set D which is strongly closed but weakly dense in U. Okay, so this is actually the case if, for instance, we are doing some numerical analysis on a variational problem. Okay, so let's imagine that we are considering just functions that are in some LP space that are only taking values in Z. Okay, so the functions only taking values in Z are a strongly closed set, but they are weakly dense because we can let them oscillate and then we can weakly approximate any other function. Okay, so what happens? It happens that, once again, excluding at most countably many alphas for which we can say nothing, it turns out that if we have a minimizer that is not, so whose distance from the dense D, from the weakly dense D is bigger than 0, then there is no minimizing sequence in D which is weakly converging to U star alpha. Okay, so in other words, we cannot do approximations of minimizers. We cannot produce minimizing sequences by using elements coming from D. Moreover, if H alpha is weakly lower semi-continuous, and we have that for every minimizer, the distance of this minimizer from the set D is positive, then it turns out that every minimizing sequence in D has no weak cluster point. Okay, so it's really a negative result in this regard. Okay, so a typical example, as I said before, is if we choose D to be the subset of LP functions, which only takes value almost everywhere in Z. Okay, so I'm almost done. I just wanted to say trade-off invariance principle for critical points. Here we need much more structure. Here U must be a Banach space. F and G should be of class C1. And then we have to ask the regularized functional H alpha to satisfy a local Lojasiewicz inequality. Okay, so which is this technical condition here, this condition. Okay, so if we ask them what is going to happen, we have the following. So if K is a strongly compact set, then excluding at most the usual countably many bad guys, for every U1, U2 in K, we have the following. Assume that U1 and U2 are points where the gradient of H vanishes, and assume that H alpha on these 2 points is the same, then it turns out that G and, as a matter of fact, F as well are the same on U1 and U2. Okay, so please notice that before we didn't need to ask H alpha on U1 and U2 to be the same because it was for free. Because before we were talking about global minimizers, and by definition, on the global minimizers, H alpha is the same, always agree. Okay, so in the case of just critical points, we have to ask that U1 and U2 are on the same level set. Okay, and in this case, they hold. Okay, I thank you for the attention, and that's all from Matt. I cannot hear you. Is anyone talking?
Okay. Now, can you hear me now?
Yes.
Okay. So to start, thank you very much for the talk. It was very interesting remark to see this kind of results. My question is more of a curiosity.
Yes.
I wanted to know if maybe you got inspired from the Moro-Yoshida kind of approximates that one uses to build gradient flows for convex functionals, like in minimizing movements.
Yes, so we were inspired, indeed, very good point. We were inspired by a passage in the Green Book, so in the Ambrosio Giglia Savarin, when defining the minimizing movement scheme, what happens? It happens that when you do the minimization in the minimizing movement scheme, at a certain point, they claim that okay, in the case that you have multiple minimizers, you can pick any of them, and for excluding at most countably many values of the step size of the step size in the minimizing movement scheme, all the minimizers are at the same distance from the previous point where you did the iteration. Okay, so they I cannot remember if they proved that shortly, but the point is that this fact is extremely general. So probably they proved that they proved this fact using the properties of the distance. right? But after, indeed, we were reading that passage, and we said, okay, but here you're not really using any of the properties of the distance squared, indeed. So this seems really to be a very general fact. And indeed, it turned out that it's not only true, so that it's not only true for the distance squared, it's true for any function, and indeed is not true for only for positive functions. So you can take any, yeah, basically you don't need any assumption on that. And so yes. So if to answer your questions, the source of inspiration, if you want, was some arguments behind the proofs of the minimizing movement schema.
Thank you very much.
No problem.
Also from online, but they don't know because honestly,
From online in the chat, I cannot see anything. No.
I can ask a question. So Alessandro, when you were speaking about the bad values of alpha,
Yes.
to exclude, or can you say something maybe, but set can be also denser, or
Yes, yes. Unfortunately, yeah, it's a very good point. Unfortunately, here, so in the construction that we did, somehow there is some convex analysis, because essentially you can construct F. So whenever F is as a domain, sorry, as a slope in which it's flat, then we have a violation. Of course, here it was easy to set these slopes to be integer numbers, but they could be any. And even worse in the practice is if you give me a regularized functional like that coming from your favorite application, like I don't know, reduced order models or machine learning. We don't know at the moment a way of understanding which are the bad values of alpha. And it may happen, as you said, that there are not only infinitely many, but they are dense. Maybe there could even be all the numbers that you can represent in your computer. And so basically in your computer, you can only simulate cases in which the trade-off invariance principle is failing. So from this perspective, we do not have at the moment many answers. So yes, it may happen that all the bad values of alpha are in Q, and so basically, yeah.
thank you. Any other question? Okay. It seems to me that there are no more questions, so we can thank again Alessandro.
Thanks to you, and yeah, thanks. It's always a pleasure, and hope that you like that. So thanks again to you.
We hope that the next time you can come to CISA.
Yes, yes, definitely.
So thank you, Alessandro.
Thanks again, and thanks everyone for the attention. Ciao, ciao.
Ciao.